Now we'll be starting with the topic of hybridization. In the process of hybridization, the atomic orbitals of an atom intermix to form molecular orbitals. This phenomena of intermixing of atomic orbitals of slightly different energies to lead to the formation of molecular orbitals of equivalent energies is called hybridization. Let us understand hybridization by taking an example. Let us take the example of, say, carbon. As we know that the atomic number of carbon is 6 and its configuration is 1s2, 2s2, 2p2. Now if we look into the atomic orbitals of carbon, we'll come to know that the 2s and 2p atomic orbitals have the arrangement of electrons like this. Since the valence shell electrons take part into the bonding, so we are considering the valence shell electrons this time. And if we look into the 1s shell, the electron arrangement is like this. Since there are two unpaired electrons present in the 2p shell, subshell, so carbon can combine with two atoms of any of the element, but actually carbon combines with 4 atoms of any element. Why this takes place? It is because one of the electron from 2s gets transferred to 2p orbital, and so the arrangement becomes like this. Now in 2s there is one unpaired electron, and in 2p there are 3 unpaired electrons. And when this transfer takes place, the atom becomes ready to undergo bonding. And now these 4 orbitals are termed as molecular orbitals. These molecular orbitals, they have same energy and hence they are represented like this. And since during the formation of these molecular orbitals, 1s orbital and 3p orbitals are taking participation, so its name is sp3 hybrid orbital. And there are 4 such sp3 hybrid orbitals in case of carbon. And so we can say the covalency of carbon is 4. Covalency, it is the number of half-filled orbitals present in the valence shell of an atom. Since carbon has 4 sp3 hybrid orbitals, so carbon uses these orbitals to lead to the formation of any of the molecules. So from this, we can say that hybridization is the intermixing of atomic orbitals of different energies to form another set of orbitals called molecular orbitals having same energy. These orbitals which have been formed, they are also termed as hybrid orbitals. Let us have a look on the salient features of hybridization. For hybridization to take place, the orbitals participating must have small differences of energy Second, the hybridized orbitals which have been formed, they possess same energy and they have identical shapes. Third is the number of hybrid orbitals formed is equal to the number of atomic orbitals participating in hybridization. Next, the hybrid orbitals have electron density concentrated on one side of the nucleus. That means one lobe is larger than the other lobe, and hence we can say the shape of the orbital would be somehow like this. Next, the hybrid orbitals can form stronger bonds than the unhybridized orbitals. And it is so because they can undergo more effective overlapping as compared to the atomic orbital. And the last is the orientation of hybridized orbitals. It is such that they have minimum repulsion and maximum stability. That means the hybridized orbitals try to occupy such position in the space so as to have minimum repulsion among them, and this is responsible for the geometry of the molecule. Now let us see some of the hybridization, types of hybridization. As we have seen that in hybridization, atomic orbitals intermix to lead to the formation of molecular orbitals. So this intermixing could be of various types, and on the basis of that we are looking into the types of different hybridization. The very first type is sp3 hybridization. As the name indicates, in this there is mixing of 1s and 3p orbitals, leading to the formation of 4 hybridized sp3 orbitals. Let us understand this with the help of the shapes of the orbitals. Say this is s orbital, which is spherical. It is combining with 3 p orbitals, px, py and pz orbital. When these orbitals combine with each other, that is, they undergo intermixing, they lead to the formation of hybridized orbital sp3 orbital, which tend to occupy the tetrahedral shape with bigger lobes and some smaller lobes. And this is the shape of all the four sp3 hybridized orbitals formed. The shape and the energy of all the four hybridized orbitals formed would be the same. And in such hybridization, there is 1/4 S character and 3/4 P character, or else we can say it is 25% S character and 75% P character is found. We can understand sp3 hybridization with the help of an example, that is formation of CH4 molecule. As we have already seen, the carbon in the ground state is having the outermost configuration 2s, 2, 2p, 2, and in the excited state the configuration is 2s, 1, 2p, 3. These orbitals undergo sp3 hybridization and leads to the formation of 4 orbitals of equal energy known as sp3 hybrid orbitals. The number is 4. So we are having 4 sp3 hybrid orbitals in the case of carbon. Now, when carbon forms the molecule CH4, it has to combine with 4 hydrogen atoms. For hydrogen, we know the configuration is 1s1. That means it has 1 electron in the 1s orbital. Similarly, 4 different hydrogen atoms can undergo pairing with the 4 unpaired electrons of carbon, leading to the formation of CH4 molecule. And if we look into the structure of this molecule, structure is the tetrahedral arrangement would be there for the sp3 orbitals of carbon. These are the sp3 orbitals for carbon, and the shape for 1s orbital of hydrogen would be spherical. These will combine with atomic orbitals or hybrid orbitals of carbon in such a way to form CH4 molecule. The types of bond formed are sp3s for all the 4 orbitals, and hence we can say in CH4 molecule a tetrahedral arrangement would be seen with 4 sigma bonds. These are the sigma bonds which have been formed. So in case of CH4 molecule, we can say there are 4 sigma bonds formed, and the bonds are sp3s hybridized. Similarly, we can take one more example of formation of ethane molecule, that is CH3 CH3 or C2H6 molecule. Now, during the formation of ethane molecule, one of the carbon atoms having sp3 hybridized orbitals Now these are the two carbon atoms in ethane molecule which are sp3 hybridized, and now the overlapping will take in such a way that 3 hydrogen 1s orbitals will combine with 3 sp3 hybridized orbitals of one carbon. Similarly, for the second carbon, 3 hydrogen will combine and rest of the 2 will overlap with each other to lead to the formation of sigma bond. So in the case of ethane molecule, we are having 1, 2, 3, 4, 5, 6 and 7. 7 sigma bonds, out of which one sigma bond is formed due to the overlapping of carbon sp3 orbitals, while rest of the 6 sigma bonds are formed due to the C and H, that is carbon hydrogen overlapping. In such a way, the formation of ethane molecule takes place. Next is sp2 hybridization. It is also known as trigonal hybridization. In this, there occurs intermixing of one orbital of S and 2 orbitals of P. This structure is like this: S, Px and say Py are combining, resulting in the formation of sp2 hybridized orbitals, where the lobes lie at an angle of 120 degree to each other. In this, we can see 1/3 is the S character and 2/3 is the P character. We can understand this with the example of BF3 molecule. In BF3, the ground state configuration of boron with atomic number 5 is 1s2, 2s2, 2p1. And the arrangement of electrons is like this. In the excited state, one of the 2s electron get excited to 2p orbital, leading to the formation of 3 orbitals of equal energy. One of the orbital does not occupy any electron, it is vacant. It do not take participation in hybridization. So we have 3 orbitals which are sp2 hybridized. These 3 orbitals have equal energy, same energy and the same shape. Now, if we look into the configuration of fluorine, its configuration with atomic number 9 is 1s2, 2s2, 2p5. In 2p subshell, the arrangement of electrons is like this. Here, one electron is unpaired. This unpaired electron can undergo pairing with unpaired electron lying in the hybrid orbital of boron molecule. Similarly, two more fluorine atoms can combine to lead to the formation of BF3 molecule. If you look into the structure of this molecule, the structure would be like this. Boron having arrangement of orbitals in the trigonal fashion, and with this the 2p orbitals of fluorine will combine. Boron has all the three sp2 hybridized orbitals, and in case of fluorine it is 2p orbital, forming 3 sigma bonds.